Hello everyone. Today my topic is a non-linear equation in the subject of the wireless communication and networks. Myself, Mr. A. Karthik, Assistant Professor, Department of Electronics and Communication Engineering, Aeronautical Engineering, Hyderabad. Okay, today topic is a non-linear equation. Okay, in the previous class also we discussed about the what is the equation, what is the diversity, what is the channel coding. Okay, after that we go for the survey of equation. That is nothing but is a classification of equation. In that also we have divided into two parts. One is a linear equation, one is a non-linear equation. In the previous class mainly we discussed about the linear equation. Go to the previous class, then you can understand the what is a linear equation. But coming to today topic is a non-linear equation. With the help of these equation, we can go with the some mobile device for reducing the distortion of the received signal. This is a student can learn from this topic. Okay, coming to classification of equalizer. Here you can see what is a equalizer. It is nothing but a compensate of the intersymbol interference. Okay, again it divided into two types. One is a linear equation and second one is a non-linear equation. Okay, this one already we discussed in the previous class. Just briefly I can explain right now. Then we can move on to the non-linear equation. Okay, linear coming to two types of structure. One is a linear transversal equalizer. This is a linear transversal equalizer. And second one is a linear lattice equalizer. That is two types of structure. Coming to non-linear, we having the three types of methods, non-linear equalization methods. One is a decision feedback equalization, maximum likelihood symbol detector, maximum likelihood symbol estimator. Okay, these are the three structures. One is a decision feedback equalization, and second one is a maximum likelihood symbol detector. Third one is a maximum likelihood sequence estimator. These are the three non-linear equalizer types. Coming to structures for the non-linear equalization, one is a non-linear transversal equalizer, and second one is a non-linear lattice equalizer. Third one is a non-linear transversal channel estimation. These are the structure for the non-linear equalization. Okay, we having the equalizer structures and also non-linear equalizer structure. Coming to algorithms. Coming to algorithm for the linear equalizers, we're having several different types of algorithms for the linear equalizer and as well as non-linear equalizer. The first one is a zero forcing algorithm, least mean square algorithm, recurrent least square algorithm, fast recurrent least square algorithm, square root recurrent least square algorithm. Okay, coming to lattice algorithm is a gradient recurrent linear square algorithm. Coming to non-linear algorithms, same as the same linear equalizer, but we're having the transversal structure. We're having that least mean square algorithm, recurrent least square algorithm, fast recurrent least square algorithm, and also we're having the square root recurrent linear square algorithm. Coming to lattice, the gradient recurrent least square algorithm. Coming to transversal channel estimation, we're having the four types of algorithms. One is a least mean square algorithm, recurrent linear square algorithm, fast recurrent linear square algorithm, and square root recurrent linear square algorithm. These are the types for the classification of equalizers. We have the two types of equalizer. One is a linear equalizer and second is a non-linear equalizer. And also coming to structures, a transversal and lattice. Coming to non-linear structures, transversal lattice and transversal channel estimation. And also dividing the three types of non-linear equalizer. One is a decision feedback equalization, and second one is a maximum likelihood symbol detector, and third one is a maximum likelihood sequence estimation. These are the types for the non-linear equalizer. In the previous session, we discussed about the equalization. There we discussed the what is a linear square and also lattice. What is a transversal equalization we discussed in the previous class. Okay, what is the difference between equalization of the linear and also non-linear? In the coming to linear equalization, we are not using any feedback path, but coming to non-linear equalizer, we are using the feedback path for the output section. Coming to non-linear equalizer used in applications, the channel distortion to solve for linear equalizer to handle. That is a main advantage for the non-linear equalizer. And also whatever having the non-linear equalizer do not perform the well on channels which need the spectral nulls in the passband, then we can move on to the non-linear equalizer. This is a good perform to the channels to the spectral nulls in the passband. And we can compensate for the distortion the non-linear equalizer places too much gain to vicinity of the spectral null, thereby enhancing the noise present in the frequencies. That is a one in the linear places. And three different non-linear methods have been developed which after implement of the linear equalizer. Actually first we are having the linear equalization, then we have some process, then we having some enhancement, the effective development of the linear equalization. We're having the three types of non-linear equalizer types. One is a decision feedback equalization, that is also we can know as DFE. And second one is a maximum likelihood symbol detection, that is a MLS. And coming to third one is a maximum likelihood sequence estimation, that is a MLSE. These are the three types of non-linear equalization. The first one is a decision feedback equalization. In this one, the name itself, feedback equalization. Okay, the decision feedback equalization, the based on the addition from the feedback, that is the main thing, that is from the topic. Okay, you can see what will happen in the feedback equalization. That once an information symbol has been detected and decided upon the inter-symbol interference. Actually, why we come for the equalization? Equalization is nothing but it compensates the inter-symbol interference. That is the main motive of the equalization. That purpose only we go with the equalization. It compensates the inter-symbol interference that can induced and future symbols can be estimated subtracted after before detection of subsequent symbols. The decision feedback equalization can be realized in either direct transversal from or as a lattice filter. This is using of the decision feedback equalization. Okay, here it consisting the two filters. It consisting the two filters. One is a feed forward filter. One is a feedback filter. That is a feed forward filter. Another one is a feedback filter. Whatever having the feedback filter, a decision on the output of the detector, that based on the feedback filter, that is output, that based on the feedback filter. And also its coefficient can be adjusted, cancel the inter-symbol interference on the current symbol, and also with having the past detected symbol. The based on the two symbols. The based on the two symbols. One is the current symbol, and also we go with the past detected symbols. The based on these two, we can adjust it to cancel the inter-symbol interference. Whatever having the equalizer having that N1 plus N2 plus I1, the tabs in the feed forward filter, and also another tabs N3 feedback filter. The output expression is the d cap of k equal to summation of n equal to minus 1 to n, because these are the two tabs N1 and also N2. Okay, but coming to feedback filter tab is the N3, but the expression come from the output expression, this one. And also we're having the CNF plus YK minus 1 plus summation of I equal to 1 to N3. Here we can use the another tab. Okay, the Fi dk minus I. This is the output expression for the decision feedback equalization. Coming to here, you can see what are the input signal, what are the coefficient, what is the output for the these non-linear equalization type of the decision feedback equalization. Coming to here, we can see this is the input signal, the yk plus n minus 1. Sorry, yk plus n1, and after that yk plus n minus 1. These are the different input signal given to the particular equalization. And here we can see the coefficient. These are the c n minus 1, n1, n minus 1 plus 1, c naught, and n2 minus 1 and n2. This is a series of the coefficient we can given to the particular input signal. Okay, these are respective input signal we can given the these particular coefficient to the particular equalizer, and whatever having the input signal and also coefficient, this input signal and this coefficient we again given to the particular feed forward filter. From the feed forward filter, whatever having the all the input signal and coefficient given to the summer. From that we can given to the threshold. Okay, from that we can give into the threshold value. Okay, before threshold we can find out the both whatever having decision from the feed forward filter and also decision feedback filter. Here we having the current symbols. In this one we are having the current symbol. Okay, in this one we are having the current symbol. From this one we can having the past symbols. In that we can find out the past symbol. The both the symbols what are having the current symbol and also past symbol we can given to the number. That is here we can get the some threshold value. Whatever having the taps from the N1, N2 and also N3, we can go with the threshold value. This is our output. Okay, here the d cap of k equal to we're having the current symbol plus past symbol. We can find out the both current symbol plus past symbol, then we can get the dk. This is our current output. Okay, from that decision feedback equation we can go with the this type of compensating the inter-symbol interference. Here we can give the multiple input signal. For that we can generate the some coefficient. From that all the coefficient and also input signal values given to the feed forward filter, and also whatever having the feedback filter, from that outputs also given to the threshold value. Then we can get the accurate output of the particular decision feedback equation. Then we can move on to the what will happen in that. What are the taps in the lattice implementation? Okay, in the lattice implementation the decision feedback equalizer equal to the we're having the length, that is n2, where it is having the n1 greater than n2. Another decision feedback filter proposed by the Bellifour and also Park is called predictive decision feedback equation. Okay, this is another form. Okay, in the previously we discussed about the what are having the coefficient from the current symbol plus past symbol, that is the decision feedback equation. We have the another format of the decision feedback equation, that is proposed by the Bellifour and also Park is called predictive decision feedback equation. It is also consist of same as the previous one, but coming to here feed forward filter as in the conventional DFE. However, whatever having the feedback filter driven by the input sequence formed by the difference of the output of the detector, the output feedback filter, that is the predictive decision feedback equation. Here you can see whatever type. Previously we discussed about the normal decision feedback equation, but here we having the predictive decision feedback equalizer. Here you can see the feed forward filter and also you can see feedback filter, but you can see the received signal samples, the whatever having the received signal samples given to the feed forward filter. Here we having the current samples. Here we having the current samples, that whatever having the current samples we can give on to the summer. Here see here this is a current symbols and these are the past symbols. Okay, again it can go with the addition device, same thing we can get the dk. Okay, here we having the d cap of k. Okay, then we can go with the output decision. Here what will happen, we can find out the previous symbols for the next sequence. Okay, actually this is the actual output out from the initially we have this some output decision, and again same output decision we can compare to the next samples. Nothing but that is a feed forward samples. Here again having the some prediction, whatever having the output prediction given to the next values to the feed forward filter. Then we can get the decision device, that is a predictive decision feedback equation. Mainly in this one we have to discuss about the decision feedback equation. Here we having the these are the structure for the decision feedback equation, and the next one is some proposed another one, that is a Bellifour, that is a predictive decision feedback equation. Here also same we get the output decision as a compensating of the inter-symbol interference. Next one is a maximum likelihood sequence estimation equalizer. Maximum likelihood sequence estimation equalizer. Here we can go with the maximum likelihood sequence estimation based on the linear equalizers. It described previously in the optimum with respect to the criterion of the minimum probability of symbol error. Okay, in the previous one, decision feedback equalization, we had some symbol error, that is from the current symbol error, or also we can go with the past symbol error. Then we can given to the channel does not introduce any amplitude distortion. Then we can that condition which an equalizer need to mobile communication link. The limitation we can with the maximum likelihood sequence estimation, the based on the equalizers. That investigation nearly optimum of the nonlinear structure, and using these impulse response simulator within the algorithm, we can provide the maximum likelihood sequence estimation. Whatever having the symbols, we can go with the all possible data sequence, by in that we're having the rather than the decoding each received symbol by itself, and also choose the sequence with the maximum probability as the output and the equalizer. Here you can see the structure of maximum likelihood sequence estimator, that is a adaptive maximum filter. What are having the channel output. Here how we get the y of t. How we get the I of t means in the previously we are having the sample signal. From that we can take the x of t plus nb of t. Okay, here this is a input signal, this is a noise signal. Then we can give it to the matched filter. Here the channel estimator, whatever having the channel estimator, it is sequenced from the output as a previous maximum likelihood sequence, and also current input we can give it through the matched filter. Then we can find out the some sequence estimation with the help of the adaptive matched filter. For example, if it is a sequence is not matched, we can adding the sequence to the we can add the sequence from the previous signal. Then we can get the correct accurate sequence estimation from the data. This is a maximum likelihood sequence estimation. And also, what are the algorithms for the adaptive equalization? Adaptive equalization compensate for the unknown time varying channel, and also specific algorithm, the adaptive equalizer coefficient track and channel variation. The wide range of algorithms exist to adapt the filter coefficient. And also, what are the having the development of the adaptive equalizer, adaptive algorithms, it compensate the it takes to delay into the great deal to how to is done, and also treated in development algorithm. These are the various factors for the nonlinear equalization. One is the rate of convergence, misadjustment, and computational complexity, numerical properties. These are the algorithms written by the various functions. The first one is a rate of convergence. This is defined the number of iterations required for the algorithm. Mainly, it having the number of iterations need for this rate of convergence. And also we have the some responsive stationary inputs to the converger close enough to the optimum solution. And the stationary environment unknown statistics, whatever having the unknown statistics, we can find out from this rate of convergence. Next, second one is a misadjustment. In this parameter, the provides a quantitative measure of the amount by which the final value mean square error averaged ensemble of adaptive filters. Then we can give the optimal mean square error. And the next one is a computational complexity. What are having the number of operations required to make a one complete iteration of the algorithm. That then we can find out the computational complexity. And we having the another one, numerical properties. When an algorithm is implemented numerically, inaccuracies are produced due to round of noise and representation of errors in the computer. These kind of errors influence the stability of the algorithm. We're having the totally four. One is a rate of convergence, and second one is a misadjustment, and third one is a computational complexity and numerical properties. Okay, these are the properties for this one. And also we're having the one coming to problem based on the nonlinear equalization. We're having this. Consider the design of US digital cellular equalizer. It having the frequencies are 900 megahertz, and also mobile velocity is v equal to 80 kilometer per hour, and determine the following. We have to find out the maximum Doppler shift, and also the coherence time of the channel, and also we can find out the what are the maximum number of symbols that could be transmitted without adapting the equalizer. Assume that symbol rate is 24.3 kilo symbol per second. Okay, here whatever information given in the problem, we have to see first of all. That is a US based digital cellular equalizer. Okay, and the frequency is the f equal to 900 megahertz. Okay, and also velocity small v equal to 80 kilometer per hour. Okay, that is a given data from the question. We have to find out the maximum Doppler shift. Okay, maximum Doppler shift means we can find out in the previous sessions, that is from away from the transmitter and also towards from the transmitter. Okay, those are the two conditions for the Doppler shift. And also we can find out the coherence time of the channel, that is a TC, and also the number of maximum number of symbols that could be transmitted without adapting equalizer, that is we can find out the total NB, the nothing but a number of symbols. Okay, we have to find out these three. Okay, this is a given data. Okay, first of all we have to find out EA, that is a Doppler frequency equal to velocity by lambda. Okay, velocity by lambda. What is the velocity they given? 80 kilometer per hour. 80 kilometer per hour. 80,000 per hour. Kilometer per hour. And also we can find out the lambda. Okay, that is a wavelength 1 by 3 meters. It can be 66.7. Okay, and also next we can find out the B. This is nothing but a hedges. Frequency is nothing but a hedges. And second one is the coherence time of the channel, that is a TC. We have to find out what is a TC equal to under root 9 by 16 pi f square d. Okay, we know it. What is a d and what is a f square? We can substitute here 0.423 by 66.67. That is from the FD. Then we can find out the 6.34 millisecond. This is the coherence time. And also we can find out the number of symbols, that is a NB. NB equal to rate of symbols plus coherence time. What is given here in that one symbol rate, that is a 24.3 kilo symbols. Okay, here the given is the RS equal to 24.3 kilo symbols. Just think we can find, we can substitute here 24,300 into 0.00634. Then we get the 154 symbols. Then we get the 154 symbols. Okay, they given in the question. We have to find out the maximum Doppler shift and also coherence time of the channel and the maximum number of symbols that detected by the symbol rate, that is a 24.3 kilo symbol per second. Here the given data, the frequency equal to f equal to 900 megahertz and the velocity equal to 80 km per hour and symbol rate equal to 24.3 kilo symbols. Those values you can substitute in this one. We have to find out the Doppler frequency, that is a maximum Doppler frequency, b by lambda, the velocity by lambda length, wavelength. Then we get the 66.67 hedges frequency and also coherence time equal to 9 by 16 pi f square d. Then we can calculate it like that. After simplification, 0.423 by 66.67 equal to 6.34 millisecond. And also we can find out the maximum number of symbols, that is RS into TC. This is given from the problem. That is 24,300 into 0.00634. That we can find out the 154 symbols. Okay, this is a solution for this problem. Okay, mainly in this in the today class we discuss about what are the classification of the equalizers, what are the different types of equalizers, and from that we can find out what are the different types of structures in the linear equalization and also coming to non-linear equalization. And after that we can discuss about what are the different algorithms in the linear equalization and also non-linear equalization. Coming to today's session, mainly we discuss about the non-linear equalization. In the non-linear equation, what are the different types of non-linear equation? The first one is a decision feedback equation, and second one is a maximum likelihood symbol detector, and third one is the maximum likelihood sequence estimation. These are the three types of non-linear equation, and also coming to different algorithms influencing to the non-linear equation, that is also we discussed. The mainly decision feedback equation, we're having the two types of filters. One is a feedback filter and second one is a feed forward filter. The based on the decision from the feedback filter, then only the output will be occur from the decision feedback equation. After that, we are move on to the this problem. Here we can find out the maximum Doppler shift and also coherence time of the channel, and also maximum number of symbols discussed in this nonlinear equation. In the tomorrow session, we can discuss about the another different types of another one, that is a maximum symbol detector, and also maximum sequence estimation also we discuss in the tomorrow session. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.